Okay, let's get started building a simple project using Xilinx Project Navigator for a basic sum of products circuit, something we start out with in CECS 201. So I'm assuming you've got Project Navigator open. We go to the New Project button. We're going to have to give it a name, and you're going to have to put it project in a certain directory. That depends on your operating system and your computer that you're working on. I happen to store all my files under a Xilinx projects folder on my data drive, and in the 201 directory I place all my projects. So I'm just going to title this Basic Sum of Products. That's the name of the project itself. Hit Next. The Nexus 2 board that we use in our class uses a Spartan 3E chip. You're going to have to make sure that's selected. The device type is the 500E. All of these are very important parameters. The package type is FG320. Later on that'll be very important. Similarly down here you want the synthesis tool, the simulator, the preferred language to be as you see it on the screen here. Hitting Next and Finish takes a couple seconds to create the project. Okay, in this pane of Project Navigator are the source files in my project, and based on the source file that's chosen you'll have certain processes down here in the bottom pane that will be available. At this point I don't have any source files, so I right click on that little chip icon there, click on New Source, and these are the different kinds of sources we'll be using this semester, but since we're doing a basic type project we choose Schematic and give it a name. You know, best convention is something that is descriptive. Use underscore instead of spaces is always safer. And then hit Next. And Finish. After a couple seconds the schematic editor window will be opened. So this is what we see on the screen. I'm going to go over and get some basic symbols. So the first thing I'd like to place in my project are the inverters for my inputs, or NOT gates. I hit Control R so I can rotate the gate, so I can have vertical wires going down my page that'll be my inputs. I'm showing a Word document here that's going to have the truth table for my basic function. So it's a basic 3-input function. It's the sum of minterms 1, 2, 4, and 7. Right here, 1, 2, 4, and 7. And here's the Boolean expression of that logic that's in that truth table. So that's what we'll be building over here. I've got 3 inputs that needed inverted. In the schematic editor, if you highlight a certain area and press this zoom key, you zoom exactly into that box. If you hold down the Control key and use the mouse cursor bar, you can also scroll in and out. I'm going to just pick up that inverter and get them all being in the same place. Zooming out. I'd like to put input A here and have that primed input B and C, so I'm going to the wire tool, and this will be my input A. This will be input B to that inverter and input C to that inverter. Now right now they're just wires, so this is the I/O marker tool that we put on those wires, and we'll rename them in a moment. Go to the cursor tool. I'm right clicking on that I/O marker, rename the port to A. Right click on that marker, rename him to B. Right click on that marker, C. Okay, let me zoom out a bit. Now I'd like to add wires to those inverters, so I'm going to go straight down the page as such. So these 3 wires going straight down the page will be the complements of my inputs A, B, and C respectively. This will be the uncomplemented version of input A. B, and C respectively. Now I'm ready to go get my AND gates. Now since I am doing a sum of minterms and I've got 3 inputs, I'm going to need the AND 3 gate. So I type in the name, and that's all I see over here. Control R rotates it to the proper orientation, and I have 4 minterms, so I'm going to put my 4 gates right down on the page there. Since I have 4 minterms, I need a 4 input OR gate, OR 4. Right there will be sufficient. Back on my wire tool, I want to take the output of this gate and to the input of that OR gate, so I'm going to zoom in. It's always best. Whenever the wire tool is over a terminal, you'll see the little 4 boxes there. If you're not on the terminal, don't click yet. So I'm on the terminal, I go terminal to terminal. Puts those nice orthogonal lines in there. While I'm here, put my input-output marker on that terminal. Right-click, rename port. I think we called him F1. Zooming out, I'm hitting the control key with my mouse. So I want this product to be minterm 1. This was minterm 2. Let me go back and check that for sure. Yeah, 1, 2, 4, and 7. Minterm 1, minterm 2, minterm 4, minterm 7. So minterm 1 is A prime, B prime, C. So I already know this wire here is A, B, C respectively, and A prime, B prime, C prime. So it's very easy and very neat to just pull straight back from the terminal. Let me zoom in a bit so we can see. From the terminal, just pull your wire straight back horizontally. It makes a nice clean connection. B prime, so easy to find because of the layout of the vertical wires. That would be B prime. And now I want C unprimed. That's the vertical wire right there. Next minterm, minterm 2 is A prime, B, C prime. Now you can see why we have those vertical wires going down the page. It makes it so clean to just pull back to the wire. Didn't quite make it. I gotta have a connection. So the square box there indicates a connection. If you don't have a square box, then you don't have the connection. Minterm 4 is A, B prime, C prime. Again, I missed the wire, so I just go back to a click on it and pull it a little further. My last minterm, minterm 7, is all the inputs in it. They're unprimed. Values. I'm hitting Control S. I save it. You should do that often. Now I'm zooming out. Again, hold the Control key and use your mouse scroll bar. That's the complete schematic right there. If I wanted to move it, I could highlight the whole thing, and you can drag them around and position it appropriately. But that is our logic right there. Now I have a habit of annotating, I think it's a good habit, of what these minterms are on the schematic itself. So I could just go to the text tool. The size has to be about 48 or above to be able to read it. And you just type in the values. So I'll say this is A prime, B prime, C. And just place the text kind of near that gate. And I had minterm 2, which is A prime, B, C prime. Place that there. Minterm 4 is A, B prime, C prime. And it's just a way of visually letting yourself know what you thought those products were supposed to be when you have to debug your logic later. Again, those are just annotations. The other thing we typically do on a schematic is add in a header box, or a title box is what it's called, down in the lower right hand corner of our schematic. That way we can place our name in there. So I'm going to zoom into this area. Okay, now down here in the title box, if you would right click on it, go to Object Properties, you can go down to the title field and the name field and change those attributes. So the title field, I'm going to highlight, put a couple spaces, and put CECS 201, couple dashes, basic SOP. And then in the name field, go ahead and highlight that, a couple spaces, and then put your name, R.W. Allison. And just hit OK. Now on the sheet, title, CECS 201, basic SOP, and my name, Rob Allison, R.W. Allison. The date is going to be whatever today's date is. And so that just gives the schematic your ownership. Okay, I'm saving the schematic. Before I leave the schematic, I want to come over here and just check that all my wires are hooked up correctly, and you should see the no errors or warnings. If you have errors, then you'll get messages down here. You'll have to make the corrections by wiring them correctly. Okay, I'm closing the schematic editor now that my simple SOP is built. Okay, back in the source files window, my hierarchy, I've got my schematic as a source file now. Now what I'd like to do is just run a basic simulation and verify that my logic diagram gives me the correct outputs as were in the truth table. So I need to create a file that places these values in for my inputs. They're known as input vectors. Over time, I'd like to change the value of the inputs to those 8 values, and then run a simulation and see if I get the proper outputs. So to do that, I highlight the schematic diagram source file, click New Source, and now I go to something called a Verilog test fixture. My convention is usually give it the name of the function that I'm testing, SOP, with another underscore TB for test bench. Select the source file that I want to test, which in this case is just the only source file that I have. So now it creates a shell, a empty shell, for me to place in the appropriate values over time. So for this semester, we're going to delete this end if, delete this if def, and create something that looks very much like our truth table over here. So I'm going to use the concatenation operator, that's the brace, and kind of group these 3 inputs all together, close the brace, and say that those 3 values are equal to 3 bits of binary 0, 0, 0. And I'm going to leave them at that state for 100 nanoseconds. So that's the first row of my truth table. Now I'm going to highlight that, copy, paste it right in here, and change the input value to 001. And I'm going to proceed to do this. Let's do 4 rows worth. And change the truth table value appropriately. 0, 0, or 0, 1, 0, and 0, 1, 1. Now if I highlight that again, just saving a little time, paste that in. The only thing I have to change is the most significant bit. Over here I'm going to put the comment, time equals 0, 0, 0 to 100. Because that first row will have the inputs A, B, and C be 0, 0, 0, and I want that to last for 100. Then the next row, it's going to be pattern 0, 0, 1, and that will be from 100 to 200. This just annotates what's going on the different times. The next pattern will be from 200 to 300 and so forth. And again, this is just so that anybody who looks at this test bench knows what the values are from what times I've got them placed there. 400 to 500, 500 to 600, 6 to 7, 700 to 800. That is all the possible combinations for a 3-bit input. And my habit or practice, on the last one I'll let all the inputs return to 0 from 800 to 900, just to kind of complete the cycle, so to speak. Oh, that's 800 to 900. So what I've done is just edited this section of the automatic test bench file, or the shell that they gave me. That's all you have to do. Everything else you just leave the same as per defined. So I've got my 8 possible combinations, 0, 0, 0 to 1, 1, 1, and then I have it returned to 0. Control S to save, and I can close that file. Now, in the View tab, you've got 2 options, Implementation or Simulation. And now that I have a test bench, I want to simulate the test bench. You have to click the little radio button. Now in the Sources window, you have your schematic test bench file, and underneath is the actual schematic file. If I pull this over, you can see the names. So this is my test bench that I just created, and it is going to test what's underneath it, which is the schematic. Very critical that you highlight the test bench file before coming down to the Processes window and running the simulator, which is this icon right here. It's a very common rookie mistake to have the schematic selected and then run the simulation and get not the desired output you want. So you're on the test bench, come and double click on Simulate Behavioral Model. That will start the simulator, which is a separate function under Xilinx 12 and above. Actually runs a separate process. So it's currently booting up. Here it comes, called iSim. Okay, first thing we want to do is change the length of the simulation. So I want it to go to, since I have 8 patterns, I want it to run out to 900 nanoseconds. You have to type in nanoseconds. I'm going to say restart and then run to that value, run to 900. Now it looks like all the outputs are all zeros, but that's because I need to zoom out for the full simulation. They list the output on the top. I'm going to pull it to the bottom and take a look at the simulation. So what I see across the screen from 0 to 900 are the input values at any point in time and the respective output value, which is RF1. So scrolling back to the very beginning, click anywhere in this first 100 nanoseconds, you can see the inputs are 0, 0, 0, and the output is 0. If I move over into this area from 100 to 200, the input value, as in the truth table, is 0, 0, 1, and as we expected, the output is F1 because we wanted min terms 1, 2, 4, and 7. You can move the cursor over to here. That's the 200 to 300 range. Input is 0, 1, 0. Output is 1 as expected. Over here, 0, 1, 1 in the truth table says we're supposed to have an output 0, and that's what we get. So I'm taking these values in the output columns, making sure that for the input pattern I get the correct output. That's what verification is. Over here, input value 1, 0, 0, output value 1. That's what we expect, min term 4. Min term 5, we didn't have it highlighted in the truth table, 1, 0, 1. Output is 0. Min term 6, 1, 1, 0, output 0 as we expect. Minterm 7, 111. We did want minterm 7 to be true, and it is true, and then this is my wraparound to the initial values. So my simulation is telling me, or verifying to me, that the function that I created in the schematic editor did work. So I can close down the simulation. You could save it if you want to, because it's going to ask me if I want to save it. So I'll just name it Basic. Give it the same name as my project. Just save that. Close down the simulation. Yes, I want to exit. Come back to Xilinx. So I've simulated. Don't have to make any changes. So now I flip back to my implementation. Now that I've verified the simulation, I come back to the implementation section in Project Navigator, and I need to associate the inputs that were on my logic diagram and the outputs with the pins on the FPGA that I'm using. So since we're using the Nexus 2 board, I need to go to wherever you have the template file, Nexus 2 500E template. For the UCF file, I'm going to copy that into my actual project folder, Basic SOP. Just paste that right into that project folder for this next step. Back in Project Navigator then, again, implementation section, right click. Now I say add source, and I click on that UCF file, which is a template. It adds it into the project. I expand the tab, click on the Nexus 2 template file, go under user constraints as a process, and I'm going to edit that file. These are all of the inputs and outputs on the Nexus 2 board. We've got the 8 slide switches, 0 through 7, the 3 push buttons, 0 through 3, the 8 LEDs for outputs, 0 through 7, and the 7 segment display, the RS-232 pins. The clock, when you have synchronous logic, is up at the top. For a very simple SOP, all you're going to do is change these names to whatever is in your logic diagram. So I'm going to use the first 3 slide switches for inputs A, B, and C respectively, and then uncomment it, delete that little pound sign so that you are actually using those inputs. I'm just spacing them over for looks, just cosmetically. Have them line up with the others. 3 inputs, A, B, and C. My one output will be on this LED down here, F1. Has to be the same name as it was in your logic implementation. In our case, that simple schematic. Again, you have to delete the pound sign in front of it. So all this file is used for is to associate your actual logic names that were in your top level module, inputs and outputs, with the pin numbers that are on the part. So we're just changing the names. I save the file and I can exit that. That's a very critical step. Now I select my top level schematic, go to generate programming file. This is to actually generate the logic to be built into the board. Process properties, we need to change our startup options on the FPGA clock to JTAG. Don't forget that step. That's to be able to program the board with our logic. After that, you can right click, generate programming file, and choose run. So it runs through these steps of synthesize, implement, and generate programming file. If you ever have an error at any step, then that's a whole nother lesson on how to correct your errors. But at this point, I should not have any errors. And you'll be surprised, it takes a few minutes because it's doing quite a lot of work to synthesize and to route your logic into the FPGA that we're using. So you have to be patient, depending on how slow or fast your system is. I'm letting it run real time just so you can see it's taking upwards to 30-40 seconds. Still going. Still going. Green check marks mean the process passed without warnings or errors. A yellow box with an exclamation point in there would mean that there are warnings, and a red box with a white X in the middle of it means it was a fatal error. You're going to have to correct the errors. You may ignore the warnings, but it's always best to look at them and inspect them and see if what it's warning you about is acceptable or not. Go over to the design summary, say show the warnings and show the errors. Notice that I did get under the map section some warnings. So under the error and warning section in the design overview, I go to map messages and I can see no variables are currently set. Okay, thank you for warning me about that. I'm okay. All the single-ended outputs in this design are using slew rate limited output drivers. Thank you for warning me about that for this semester. That is okay. So those warnings I may ignore. Again, it was under the map section. It's always good to look at the warnings and see if that's okay. You'll get comfortable with which ones are acceptable and which ones aren't. At this point, I've generated the program file. If I go out to my project folder now, I have a bit file that just got created, and that is what we will download into the board, which will be another lesson at another time. So that's about all we want to do today. I've created a new project. I've created a schematic in that project. I have simulated that particular schematic with the simulation tool over here. And then I edited my UCF file using the editor to associate my inputs and outputs. After I did that, I went through the process of synthesis, implementation, and generated the program file to create a bit file to download. So that's all we want to do today. See you next time.